Okay. So I'm going to try to really focus pretty purely on what we do with Biorock technology and how I think that fits into the effort to reverse climate change, which we all agree has to be done urgently, and we're all afraid might not happen in time. Really afraid of that. Okay, so what I'm going to do, I'm going to share my screen. I'm just going to show you pictures from a PowerPoint presentation that show about our technology, and it's a lot of stuff. I'm going to jump around in it a bit. A dangerous thing to do, but what he found is that if you run a direct current through steel structures, a low voltage direct current that you can't even feel through steel structures, something pretty amazing happens. I mean, it sort of is known from other contexts. First of all, you stop all rusting on the steel. This is a version of electrical, methods to prevent rusting on, say, oil rigs and bridges. And people just give it a trickle of charge, and that just poisons the metal in such a way that it won't react with oxygen, so the steel remains intact. And but if you apply the current a little higher, something even more interesting happens. That was discovered originally by Michael Faraday. In seawater, you begin to precipitate limestone. Now, this piece that you see here is a piece of material that we grew in the Maldives, and it's about a year or two of work. The iron bars, the size of my little finger or so, and what he found is you can grow limestone. This is, of course, the rock the pyramids are made from, and it'll last for hundreds of thousands of years. So it doesn't happen naturally in nature. Limestone does not precipitate out of the ocean, even though it's supersaturated. And thermodynamically, it should precipitate, but it doesn't for kinetic reasons. And so organisms, in order to form their shell, spend a lot of their metabolic energy pumping ions back and forth across membranes in order to precipitate limestone. But it does not happen by itself. So Wolf Hilbert's found that with a little trickle charge on this stuff, you overcome all those kinetic barriers and you grow solid rock on top of steel. The steel doesn't rust. And what we typically try to do is to do it not much more than 1 to 2 centimeters a year. Now, he invented this in the 70s, as I say, 1976, for architectural purposes. His goal was to basically turn the ocean into a huge mine, precipitating limestone that could be used for building blocks, walls, roofs, prefabricated architecture. That was his goal. And what he found is if he grew it between 1 and 2 centimeters, or not much more than that, the material he produces is about 2 to 3 times harder than ordinary concrete. That's compressive strength, how much weight you need to put on for it to break. So it's extremely strong, and we're able to grow it. Now, we can grow it normally. How fast it grows depends on how much current you're putting in, obviously, and the size and shape of the electrode. We're charging seawater, and this is just electrolysis of seawater. So electrolysis of seawater produces one terminal, which this is one, which is reducing an alkaline. So in other words, at this terminal, water is broken down. It takes about 1.25 volts for that reaction to take place. Water is broken down to form hydrogen gas, and that we see bubbling. We see it just bubbling into the air from these structures. That's how we know it's working. And then hydroxyl ion. The hydroxyl ion reacts with calcium in seawater and forms calcium carbonate. If you do it quickly, it'll react with magnesium in seawater, which is 5 times more abundant. And that's a very quick reaction. So if you crank it up, you produce huge amounts of magnesium hydroxide. That's a soft mineral, and that flakes off. So for structural purposes, we grow it very slowly. And most of our structures are underpowered. So some of them are growing like 1 millimeter a year. But we could grow 10 or 20 centimeters a year if we wanted, but that would be softer material, it would be different mineralogically. I'll come back to that a little later. But the key is that with this, we're able to build structures of any size or shape from steel, any size or shape. So in this case, these are pieces from the Maldives. This piece here is really heavy. And this is 2 years of growth, and it's absolutely rock hard. So what we do is we basically build structures shaped like reefs. This is a Biorock reef in Indonesia that's 4 years old. And this is one that was built where it was completely barren. It was just sand and dead coral rubble and nothing there, no fish, no corals. And this is after 4 years. We transplanted a few pieces of coral to it. And we have an entire rich ecosystem. It's another 4-year-old reef in Indonesia too. So this is where there was literally nothing before. The reef had died from bleaching, and we brought it back, completely transformed it. So, but the thing is, these structures here we build to be open mesh frameworks like a coral reef. So that way the water doesn't reflect. The reflection is what causes scour and causes erosion. So any reflective seawall or breakwater will cause all the sand in front to wash away, and then the sand under it to be washed away because it focuses the scour, and then the wall falls down. And it's a great business model for marine engineers. You know, they know it's going to fall down, will have to be rebuilt forever. Our structures work on totally different physical principles. They work like a coral reef does. There, the water flows through a porous, permeable structure and dissipates energy by internal friction. It loses energy by refraction and diffraction, not by reflection. So it doesn't cause scour, but we are able to dissipate the energy. A real coral reef can dissipate 97% of the wave energy coming in. That allows the beaches to form. So all tropical beaches are there because there are reefs in front of them. And that they also provide the sand from the growth of the organisms. So we grow reefs in front of places, we restore the ecosystem, restore the fisheries, but then the beach grows back. And so in this particular location, Indonesia, we have about 150 of these reefs. Each one is a different size or shape. Many of them, I mean, you know, the Balinese in Bali, they're artists, so they're very artistic. So, you know, the point is the function of these structures has slowed down the waves sufficiently that the village behind had a beach that was washing away, trees falling into the sea and so forth. And we grew the beach back. And that we've done repeatedly in many places around the world. We grow a reef in front of an eroding beach, and the beach grows back by itself, literally in months. I mean, in some cases we've done for a lot longer, but we've had totally eroded beaches regenerate themselves in as little as 3 months by simply growing these reefs in front. So we're able to protect coastlines from erosion. And because this material, we can grow rock hard 2 centimeters a year, we can grow these things to match sea level rise. Now, these only grow in the ocean because it's the electrical conductivity of the water that causes the process. But so we can grow right up to the high tide mark. It's only when it's underwater that it'll grow. But literally, we can build reefs that grow to match sea level rise and grow islands back and grow shorelines back. And it's the only method that works. We've done that mostly in Indonesia and in the Maldives. So let me get another feature of this is something very interesting. This is a self-repairing structure. This is a Biorock reef in Bali that was hit by a boat, smashed into it, a mooring broke. And you can see here, this is steel that has been in the water for 11 years and has no rust on it at all. And then the damage area heals itself and it grows back. So it grows new limestone, the damage area. So this is the only marine construction material that gets stronger with age and repairs itself. There's a growing structure. That's why we call it Biorock. So it has many properties. I'll come back to the physical properties a little later. So that's a close-up after 12 years in the water, and then, you know, it grows back, that's all. Okay, so here's a couple things that we do with it. This is a project that was done in the 1970s in Louisiana with solar panels. Now, we can use any form of electricity. We like solar for a lot of reasons, but we can use any form. We've done it with windmills and wave power generators and conventional electricity. And what he did here, just to give an example, is he wired up a metal basket to one of his structures. And when he came back 3 months later, it was full of oysters that had grown to adult size and settled by themselves. There was no rusting on this when he pulled it out of the water after 3 months. This thing then sat in somebody's backyard for 20 years and rusted from the rain, but it was not rusting at all when it was taken out of the water. But it also indicated that there were phenomenal biological properties of the process, that we generated a whole basket full of oysters in months. So what we've been doing mainly is since I'm a coral reef guy, but what we mainly do is we go to places like this, where the beach is washed away. We build a reef in front of it, and it grows. and like mad. And we grow the beach back. When we began, this was in the Maldives, this building was about to collapse into the sea. There was a wall of sandbags in front, and they said they couldn't possibly save it. They would have to tear the building down. And so we grew that whole beach back. Now, this beach had disappeared. So this is the Biorock Reef in front. And the other interesting thing is the year after we built this, they had the worst high temperature bleaching event in the Maldives. And the reef in front here, about 99% of the corals died from high temperature in about 2 weeks. And most of our corals that were sitting here in the hottest water, most of them survived. And so that's when we really realized that we had extraordinary biological properties of this material. So a lot of what I've focused on is the fact that we've been showing that we get orders of magnitude in many cases, but sometimes a little less, sometimes only 5 or 10 times, in some cases 10 or 100 times greater settlement of marine organisms. They're actually attracted by the electrical field. So we take areas that were barren of life and we grow whole reefs back. Let me find a before and after picture a little later. It's not just, we put corals on these structures and they grow typically 5 times faster than normal, and they survive severe bleaching events. But that's true of every marine organism. They come to settle on these sites. So, I mean, this is a beach protection reef, for instance, just forming, and in short order, corals spring up all around it, and the beach grew back. This beach had disappeared, and there you can see the reefs off on the shore, just poking out at high tide, and we regenerated the fisheries of this area. So we get tremendous buildup, and we get tremendous growth of all marine organisms. And it's, when I say all marine organisms, it includes, we attract huge numbers of fish. We grow the seagrass much faster. We grow salt marsh much faster. And I'll just give you some examples of those for coastal protection, because that's very interesting. One second, let me scroll way down here. We grow oysters faster. Let me just show you that here very quickly. These are oysters that we grew at a Superfund toxic waste site in New York City. The controls grew 5 millimeters over a whole growing season in a year. They started 20, they grew to 25. The Biorock ones grew not 5 millimeters, they grew 45 millimeters. Okay, 9 times faster in length, but also 9 times faster in width and thickness. So at vastly greater biomass. And when we grew them in winter, they kept growing all winter long. They never went dormant. The controls, 93% of the ones without electricity died. The ones with electricity never stopped growing, and they all survived. It's a severe, this is a Superfund toxic waste site, and we're regenerating them. This is an example in the Mediterranean where we're growing seagrass on bare rock. Took little seagrass plants, we put a little mesh that's powered by a trickle charge from a solar panel, and we got a whole little ecosystem, this big. Fishes, crabs, worms, shrimp, and everything moved into it. Controls all died. No one else had ever grown seagrass on bare rock before. Normally they require a lot of sediment for the roots to grow. We got mussels and oysters and fish and everything moving in. Now, here's another example here in New York City. This is our beach. It's a toxic waste dump. We planted salt marsh grass there. The salt marsh is what protects the shorelines. This is the same place we grew the oysters, powered by a solar panel that you see here. And here, the student is measuring just the height of the salt marsh. This one's getting power. These are the controls. And we got the salt marsh to grow twice as fast. We got it to grow deeper in the intertidal than it could normally grow. So we could extend the whole ecosystem seaward, where it's retreating inland. We got much greater growth underground, not just above ground and below ground. So this appears to apply to both, all forms of marine plants and animals. So what we're trying to do in many places is essentially to restore the natural ecosystem, marine ecosystem protection of coasts by regenerating these ecosystems. We've killed almost all of them with pollution. Everywhere they were near people, we pretty much wiped out our coastal ecosystems, and none of the regeneration methods work very well because the bad water quality wipes them out. Our method sort of overcomes that because our plants or our animals are growing so much faster and healthier, they're able to survive that. So what we're trying to do with this technology, it's, first of all, is to move into which is now being called blue carbon. Now, the thing is, with a salt marsh or seagrass or mangroves, the bulk of the carbon isn't what you see above ground, it's below ground. It's not just the roots that are proliferating through the ground, it's the organic carbon that's built up in the sediment. So we're able to greatly accelerate the growth of these ecosystems. Half of all the seagrasses, mangroves, and salt marshes in the world have already been destroyed. They're gone. They've been turned into CO2. Most of the coral reefs are gone. So this is the only method we know of that regenerates them quickly, greatly increases the storage of carbon, both above ground and below ground in all of these ecosystems. But also we're increasing the storage. Let me just show you a little close-up here of one of these. I mean, here, for instance, you see we're growing salt marshes. There's just a mesh that we're wiring up. And this we're able to grow at lower in the intertidal that could normally grow. So it's really quite simple. In this case, we planted 5 plants in 2007. We now have hundreds. The controls all die. We can plant all the ones we want. They wash out. They don't grow. So we're getting huge amounts of root growth. But while we're forming the limestone here, remember I mentioned that the electrolysis increases pH and hydrogen. So we're actually creating conditions on these structures that increase the storage of the organic carbon in the sediment. So that's extremely interesting. So basically, this is a method that let me put this way. I think that blue carbon is really the low-hanging fruit in the sense. So when we talk about storing carbon as organic carbon in soils and sediments and ecosystems, the soils are the biggest storage. It's 5 or 10 times more than is in the atmosphere and the biosphere. And so that's what we're really trying to do, is regenerate whole ecosystems, and they're above and below ground carbon storage, and the soil. The thing is that with marine wetlands have more organic carbon than CO2 in the atmosphere. And they occupy something like, well under 1% of the Earth's surface. These sediments are the richest soils in the world. Marine soils, wetland soils have the most carbon of any ecosystem. So it's a place that you can stick the most carbon in the ground in the smallest area at the least cost if we're trying to regenerate them. And in doing so, we regenerate coastal protection, we regenerate fisheries, and we regenerate carbon storage. Systems that are now losing carbon become carbon sinks. So we think this can be done on a very large scale, and probably would be about one of the cheapest ways of carbon sequestration as organic carbon that we can imagine. So that's one of the things we're trying to push is, and we're working with the Blue Climate Fund, which is not yet formed, but we hope. There's a lot of talk at the UN now about investing in blue carbon. No one has agreed on any framework because all the oil producing and coal producing countries will always refuse to allow the subject to be discussed at the United Nations, how to account for carbon, anything other than fossil fuels and biomass. So there's no agreed framework for dealing with this thing, but everybody senses that carbon trading is coming up, and they want to be peddling carbon credits even before they know how to grow them or how to count them. So, hopefully that will resolve itself in the next year or so. But we think that restoring coastal ecosystems and the carbon they contain is going to be a huge component to carbon dioxide removal, and maybe one of the cheapest, because really this can be done really with very little money. The other aspect I want to mention comes back to the materials themselves. So here we're increasing organic carbon at tremendous rates. And we can do this on any scale. But obviously, there is a cost, and that's providing the electricity. To put that into perspective, these beaches we grow back, typically we grow back hundreds of meters of reefs and beaches with about 3 air conditioners worth of electricity. So that's, say, 3, 4, 5 kilowatts of energy. So that's actually very little, what it takes for the ecological benefits and the carbon benefits that you get. So we're basically trying to work with people who have severe erosion problems and severe fisheries problems, and trying to work with them to regenerate their own ecosystems long term. Hopefully there'll be the added benefit later of carbon credits when that gets agreed to. But anyway, we're trying to push them to do this for their own reasons because they have to do it anyway. So let me switch gears here. Now, the other aspect comes back to the solid material. I mean, this is pretty much calcium carbonate. Okay, and we all know that calcium carbonate is a major long-term sink. Now, we have always refused to call this material a carbon sink. I've always refused for decades. I've been working on this stuff for 35 years. I should backtrack. Wolf Hilbert's invented this technology for architectural purposes in the 1970s. I heard about it in the 80s, and I asked him to come to Jamaica to work with me growing corals. And I'm from Jamaica. Corals are what I do. And he came down, and we worked for 20 years on regenerating coral reefs, and he never had a chance to get back to the structural stuff. But my view was that all limestone in the sea is a CO2 source to the atmosphere. I mean, that's the general geochemical point of view. The reason for that is that, just basically from the chemistry, is that the carbon in the water is in the form of bicarbonate. 98% of the inorganic carbon is bicarbonate. And so what happens is that when you remove CO2 by degassing or photosynthesis, what you're doing essentially is for every molecule of bicarbonate that is converted to CO2 and lost from the system for reasons of charge balance and pH, homeostasis, pH buffering, for each molecule of bicarbonate that goes into CO2, one molecule of bicarbonate is converted to carbonate ion. Okay, it's a 1-to-1. And that carbonate ion then reacts with calcium, which is much more abundant in seawater than bicarbonate, and then precipitates out. So the normal mechanism by which carbonate is precipitated in the water results in CO2 emissions, okay, an equal amount. So one molecule goes down as limestone, one goes out to the atmosphere as CO2, and therefore we've always regarded ocean limestone as being a sink of ocean bicarbonate, but also a source of atmospheric CO2. Okay, so that's always been my point of view. And so we never call this a sink. But actually, I've been thinking, I've realized that whole thinking was wrong. And the point is that in this case, we're making the high pH not by removing CO2, but we're doing it through the hydrolysis of water. So obviously the CO2 system responds to that change in pH, but in fact, a change in CO2 is not the cause of this. So in that sense, what we have to do is look at the pH balance of the whole system. We've got a positive terminal and a negative terminal. Okay, this one is a negative terminal, and it's reducing an alkaline. The other terminal is the opposite. It's acidic and oxidizing. At that other terminal, water is broken down to make hydrogen ion and oxygen. Okay. And that oxygen's good, but also some of those electrons wind up reacting with chloride ion, which is very abundant in seawater, not as much as CO2. And that winds up producing some chlorine as well as oxygen. Okay, those electrons don't contribute to producing hydrogen ion at the other electrode. So in proportion to the amount of chlorine that you produce, you're getting less acidity produced than alkalinity at the other terminal. And in fact, the net reaction is alkalinizing. You're producing more alkalinity at one terminal than acidity at the other because of the side reactions taking place at the electrode. And so in fact, the process is carbon negative. It's actually carbon negative, but fairly weakly. I mean, I don't claim this is going to reverse ocean acidification on any large scale in the water, but on a local scale, we reverse acidification because we've got pH 11 on the surface here, and we're just precipitating out limestone because of the high pH. But the net effect is actually slightly carbon negative, okay? Now, what's more interesting though, if we grow this stuff very quickly, and this is just an example here, we grow it very quickly. I said we produce magnesium minerals that are very fine, and these are examples here. These are powders that I grew. And this is almost pure magnesium hydroxide. We can produce this by cranking the pulp. We can produce this very easily in huge amounts from the ocean. The ocean has lots of magnesium. And so now this material is extremely interesting because what we're planning to do with Biorock materials, and we were trying to commercialize this on a large scale, is to grow this material, which is magnesium hydroxide, and then use this as a cement. The magnesium hydroxide, when it's wet, reacts with atmospheric CO2, and it converts very quickly into magnesium carbonate, which is even harder than limestone, calcium carbonate. considerably harder. So this winds up producing a cement. We've made bricks from it, for example, and it's harder than CO2, and magnesium carbonate is 52% CO2 by weight. So the idea is, what we plan to do is essentially make this stuff in the ocean and then use it to make a cement on land that reacts with atmospheric CO2 and removes that. Now, we produce about 1 kilogram of material for 1 kilowatt hour of electricity. So that's a cost. We've got to be putting that energy in. So that's 1 ton per megawatt hour. And so really the cost of electricity is what determines the economics of this process. Now, the things, we're getting to the point where solar power is coming down to about 1 cent a kilowatt hour. You know, it's now commercially closer to 3 to 4, but I mean, they're projecting that we're heading for something like 1 or 2 cents a kilowatt hour in the very near future. And we get to say like 1 cent a kilowatt hour, you can produce this material, you know, for about $10 a ton. Okay, now Portland cement is about $160 a ton. And then, of course, you have to add 4 times more aggregate, which is also very expensive, typically $10 to $50 a ton. So in fact, we can produce harder material in any given size or shape that we want for a lot less cost than concrete. So really, part of my ambition is to develop this as an industrial process and put a carbon negative material like this, so like the cement that we'd make from this, to replace concrete as a whole. Now, we're at the point now in 2020 where the amount of concrete and steel in buildings exceeds the whole biomass of the world. Okay, concrete is the most abundant material on this planet. And as we all know, each ton of concrete Portland cement produces 1 ton of CO2 in the atmosphere, whereas each ton of this, contains a ton of CO2 in it. Well, half of it is CO2 by weight. Sorry. So we think that's an option. And the thing is, we think, to give an example, a country like the Maldives imports Portland cement at ruinous cost, and they could be growing in the seawater their own materials that are harder for a tiny fraction would cost them to import it. So we're trying to work with the Maldivian government on developing their blue economy strategy to kind of mainstream this technology into their overall development strategy. What they're doing now is they're going billions of dollars into debt, dredging up the seafloor and piling up artificial sandbanks that are, 10 centimeters above sea level, with no natural coastal protection. With this, we could be growing reefs in front of them, growing whole islands that match sea level rise, regenerating their fisheries. That's another long story I don't want to get into here. But they could be producing their own building materials at a fraction of what it costs to import them and be contributing to the solution to the global climate change that is flooding them. I mean, it's flooding, it's destroying the whole country. Every island's washing away. And that's true. Now I work all around the world because I have dived in almost every island nation in the Pacific and the Indian Ocean, the Caribbean, and they're all washing away. Every one of them have islands that are disappearing and collapsing, and they're not getting any help. What they're getting foreign aid agencies giving them money to build concrete and rock walls on all imported materials, and every one of those walls has fallen down, many of them before they finish building them. They're halfway along and the other end's already falling down. So we think that these islands could be growing their own limestone, their own magnesium carbonate, and saving their countries as well as contributing to the solution. So that's sort of our goal with Biorock technology. Now, I mean, we are definitely regarded as a fringe technology because we're the only people in the world who've been doing this stuff for 35 years. But we're beginning to get a little attention because people are now beginning to admit that what they've been doing hasn't worked. It really hasn't. They've been throwing money away and on coastal problems, and their ability to adapt to sea level rise is even the current rate is almost negligible.
Can I just we're getting, I want to make sure we have plenty of time, or at least some time for a conversation. Maybe could you take a couple? This is incredibly. I'm so hesitant to ask you to wrap up, but maybe just kind of summarize in the last couple minutes and, what kind of support you're looking for, and then we'll open it up for a discussion?
Well, good question. I think we just want to see the technology used where it's the best solution to other people's problems. I mean, I'm a scientist. I'm trying to help people solve problems. I'm not in it trying to make money. But it's extraordinarily difficult to get people to accept new ideas, even when the evidence is right there that they can look at. So anyway, I've been trying to work with the small island developing states to get them to really do something to protect themselves. For political reasons, none really has. They've all been waiting for a free ticket out. The Maldives, no one's going to give them a free ticket. So, the other small islands might be able to get into Hawaii or Australia or New Zealand, but Maldives are on their own. And if they don't find a way to grow, it's going to be sink or swim. So we're just hope that they will, take steps to develop technologies that will protect themselves and, allow some sort of sustainable future. But otherwise, they're in deep trouble. So I'm working to some degree with the United Nations Oceans Conference and groups like that to try to see that governments start doing stuff that makes sense instead of just accepting money to do things that don't make sense, like building concrete walls. But we also want them to be, as they contributing to the carbon sink on a large scale too. There's no funding for that now.
Open it up to some conversation. Maybe you can take your slide down so we can all see each other.
Yes, I beg pardon. Yes, all right. Stop share. Right. Sorry about that. Yes.
Oh, no problem. Great. Yeah. Thank you so much. That was, I'd love to hear more, and maybe you'll come back. But let me just open it up to whoever would like to make a comment, ask a question.
Okay, actually, there's some questions here. Let me just see.
All right.
Yeah, well, the thing is this: you need people ask me, when do you turn the power off? Now, we've had structures that have been off power for 30 years, and they're completely intact. So they survive hurricanes and all that sort of thing, even Category 5 hurricanes, because they're sufficiently strong. But the biological benefits, once you form the structure, it'll last as long as the pyramids. But the biological benefits depend on the current itself, and so the fact that things are growing faster, more resistant to high temperatures and pollution, that stops if the power is turned off. So when people ask me, when do you turn the power off? My answer is when global warming goes away.
Okay.
No, I mean the sad thing is that these ecosystems are now on life support. I mean, that's the reality of what conditions we're dealing with. So if we turn the power off, and I give an example. I mean, the Maldives, we saved an entire reef from bleaching in 1998. And then they said, oh, well, we've got the reef, we've got the beach back, we'll just shut the power off. And they did. And 18 years later, they had another bleaching event, and those corals then were no longer protected, and then they died. So, maintaining the power, now it's only a trickle charge, but it's only a trickle charge. It's easily done with solar panels. So that's what we're thinking of, is people using local solar energy to grow back their coastlines and store carbon and generate fisheries all at the same time.
Do you see any connection with the kind of olivine mineralization that Project Vesta, if you're familiar with them, is trying to do?
Oh yeah, no, I'm very familiar with them.
Yeah. What's the connection or the synergies? Are there any?
Well, yes. Well, I mean, there could be. The catch is that, well, I mean, many things. I don't think olivine reacts as quickly as they hope. Let me put it that way. I mean, by and large, when you have sand on a beach, it storm washes it up. It reacts with water. It settles down, and then it's not reacting very quickly. So in other words, they're counting on it being constantly stirred up and reacting, and that doesn't really happen that way. So I don't think they're going to get the results that they expect. Olivine definitely reacts quickly. Adding calcium carbonate obviously to the deep sea would definitely work to remove deep ocean carbonate, but that's a long-term one. The olivine, I think to me, a better use is not olivine but basalt as fertilizer for plants, because then the plants greatly increase the weathering rate, like 10 times. So if you have olivine sitting by itself, and olivine with the roots growing into it. The roots are going to dissolve it many times quickly because they're pumping CO2 and organic acids into it, But olivine is not a good choice for that because although it's the fastest reacting mineral, it's also not balanced in terms of its nutritional composition. So basalt is much better because basalt contains all the elements plants need except for nitrogen.
Okay, so it looks like I'm going to ask Leslie to speak and then, or to ask question or comment, and then Peter, and then Robert. So go ahead, Leslie.
Yeah, this sounds amazing, and I'm wondering if the excuse me, if the reason that it sounds like you need funding and need acceptance, and I'm wondering if it's something like you need to find the match of patient capital with patient building, right? I mean, it's a slow process, but it's a persistent one, if I've got that right. Can you articulate what the barriers are? And besides the fact that it's a new concept and it is kind of mind-blowing, but beyond that, why isn't this everywhere already?
I wish I understood. I mean, there's a simple answer, but people are very resistant to new ideas, particularly if they have their stake in the old methods. I mean, just like the fossil fuel industry doesn't want any change to business as usual, and fossil fuel users and producers are all, trying to prevent any change to the economic system based on fossil fuels. In our case, I mean, we have people making fortunes off building seawalls that fall down. And they don't, for us, we're an existential threat because our stuff works. In terms of the building materials, I mean, essentially, I tell you what the problem has been. The reason why it never took off for building materials is simple, because if we're growing something at 2 centimeters a year, and you want a wall that's 20 centimeters thick, you're going to have to wait 10 years for that. And people don't have that kind of patience. With concrete, you pour it, and once it's dry, you can move in. So ours is a long-term solution. You're growing.
Is it diffusion that makes it go so slowly? Because there might not.
Sorry?
Are you limited by diffusion? Is that what makes it?
No. You're not limited by diffusion. The thing is that if you try to grow it quickly, you produce the other material I showed you, the soft material, the powder. See, so in fact that has enormous benefits. But what we're trying to do is start producing this material on a large scale to be used on land while growing this stuff in the sea for habitat regeneration, carbon storage, biological carbon storage, but to put the stuff on land.
Yeah, there's just a lot to think about here, and I come from a microstructures background, and so
what background?
MEMS, microelectromechanical systems, microfluidics.
Okay.
So you think about if diffusion is your problem, there could be ways around that.
Yeah, no, I don't think diffusion is really the problem. Yeah. No.
Okay.
Anyway, yes.
Yeah, I don't want to take up all the time, but I'm fascinated. Yeah, thank you.
Yeah, but anyway, I do think that, potentially this is an existential threat to the concrete business. We'd like to put them out of business, but we might not have to have them investing in it or sell out to them for that to happen. Unfortunately, that's the way the world works. We'll see.
Peter?
Okay, that'll work better. Yeah. So Tom, it's good to meet you.
Yes,
good talk. Yeah. I had to leave for a few moments, so I apologize. You probably answered some of these already, but they're simple. How much power is needed? You said it's a volt or two, and how many watts per square meter?
Well, it depends on the size and shape of the structure, really. I mean, how can I put this? We're generally operating just a few volts and 10 or 20 amps and
good.
5, 6, 12 volts. I mean, generally speaking, we're using uncontrolled power supplies, solar panels, and all of that. But they're normally producing more than we need. But we're down there. You can't feel the current in the water. It's that low.
Right, and so 10 amps would. That would be like 100 meters of seawall or something.
Well, again, it depends on the amount of steel and the size and shape and so forth and so on. But no, I would say, well, let me think. I mean, for instance, in Jamaica, we have a project with 5 domes, reefs that are about 15 feet across. And Oh, probably using, my goodness, I forget now what the power is, maybe 200 watts, maybe less.
Okay.
I mean, this is a light bulb like amounts,
Yeah, yeah. If you know me, I'm wanting to multiply it by large numbers. So I need to know what number I have to multiply by a large number. But it sounds like 200 watts was like was that
okay. I mean,
like 100 meters across?
Well, no. You see, normally we're building small reefs. In terms of the shore protection, well, let me give an example from Indonesia, where we grew a beach that was about 300 meters long. We grew it about, well, it's gotten wider and wider since we started, but it's more than 50 meters wide. It's grown up about 1.5 or 2 meters, and that was using something like about 3 kilowatts of power over 300 meters. So you would say for shore protection.
So 10 amps per meter
So it's pretty modest when you think it's less than the lights along the beach. Let's put it that way.
Sure. Oh yeah. But yeah. We're talking to a physicist here.
Yes.
we don't do small and large. We do.
Yes. Yes.
Okay. Good. How many sort of tons of CO2 or tons of carbonate per year? Again, how do you have a number for that?
No, no, because the thing is, we build. We're coming from a purely empirical standpoint. We build structures and we see what happens. And we don't actually have any instruments other than our eyes and a video camera.
No problem.
Not even a thermometer.
Yes. No apology needed.
But I mean, I will say that the process is so fascinating. It touches on every aspect of engineering, physics, and chemistry and biology. So it's really fascinating. I mean, no one really understands the mechanism by which we're getting things to grow so fast, but it's very clear that's happening.
Right. Have you worked at all with our friend Brent Constance, who does the synthetic limestone?
No. I've never met him. I've heard what he does is a version of our process. I mean, the thing is this: is that we're growing. All our work has been growing in seawater because our purpose has been to restore marine ecosystems.
Yeah, I understand. Yeah.
Yeah. So now what he's doing is something a lot of people are doing is CO2 capture, is trying to find focus sources of CO2 and develop an industrial process for that in a medium that's not the same as seawater, whatever it is they're using. I'm not sure, So we haven't played around with that, but definitely what their process is another variant of the same thing. It's just with the different inputs and different conditions.
Yeah. Well, it's interestingly similar, and they can work with atmospheric CO2. They take whatever CO2 is.
That's right. They're definitely possible. Again, because our focus has been ecosystem restoration, we've been working in the ocean always. Yeah. But the thing is that what I'm about to start doing now is doing work with desalination brines, and we produce the stuff twice as fast because it's twice as salty. So that's going to be a particular focus. And we had not been focusing on industrialization of the process, but now we're about to start doing that. And the thing is this, that also has additional benefits, because then you can trap the hydrogen, you can trap the oxygen, you can trap the chlorine. So that produces additional benefit. You can't do that in the ocean because that stuff just bubbles off and you just watch it bubble,
Yes.
But there's definitely an industrial processes that we are going to look into developing with this that are, very similar to what many other people are doing. This is a lot of other people independently discovering this too.
And what kind of money do you need?
Oh, well, good question. Basically, what I'm trying to do is set up an R&D facility to quantify and optimize the process. I mean, that means we've got to quantify all the gaseous, liquid, and solid, products simultaneously, and look at how that's affected by the rate and all that. So that's what I'm looking into. To tell the truth, I don't even know what equipment costs these days because I haven't had any for so long. So I've got to find that out soon.
Would you write up a proposal?
I'm sorry?
Would you write up a proposal and I can see who might have funding?
Well, what I'm actually in discussion with Blue investors who are very interested in this. So I have to write such a proposal. I'm not sure. There is. Let me mention this. I mean, I'm advising a group that's trying to set up the Blue Climate Fund, which is the Green Climate Fund of the UN, which is purely terrestrial. Now they recognize they have to have a marine component. Everyone's talking about, marine carbon credits, even though there's no framework for dealing with them yet. And so, but there is a network of Blue investors working with the Green Climate Fund, and they're mainly based in Geneva, Paris, and New York, but also other places, Madrid and so forth. So there's the beginnings of a coalition of people who want to spend money on the ocean. They don't know what to spend it on, so they're just sitting on it. I'm sure you know about this. We hear about all these tech billionaires, and they're so incredibly rich, and they want to save the planet, but they're not doing it because they don't know what to do with their money. I'm sure you're familiar with that, right?
Yeah.
So anyway, so we have another bunch of these, and we will try to talk to them.
Well, when you have a proposal, how soon are you planning to have a proposal for these guys?
Oh boy, yesterday. Yes, no, I'm involved with too many things, unfortunately, but
I understand. That's why I asked.
Yes, so
I'm known for that.
Yes, I've got to get down to that soon. But I mean, obviously, you are dealing with very serious investors too, and it's a very different world of the ones that I'm dealing with because I'm trying to deal with the ocean-focused ones. But I mean, essentially, they are the counterparts, and there may well be many of the same people involved at different levels. So let's talk a bit more about that. I mean, I know that everyone's searching for funding, and the funding is allegedly out there, but not being spent for the most part, if it's really there.
Yeah. There's a lot of money. I don't have it, but it's getting closer by the month. That's why I'm interested in seeing a proposal that I could show people and start things happening.
Yeah.
So,
okay. Well, let me say this. I mean, I've kind of deliberately not published anything about this stuff for years. Just been focusing on getting results. So I actually have a long paper on the carbon sequestration aspects of both the blue carbon and the materials that I wrote, and the reviewers sent it back saying it needed more work, and I haven't had the time to look at the reviews. So I don't know what it is they wanted, but I can already see a lot of ways to improve it. So I'm sure their input is going to be useful. So that's my fault, but I don't really have anything published on this at all that's written down. Yeah. So that's my fault, and I need to do that, and I need to do that very soon. So let's keep in touch, because obviously we're all trying to restore the planet. We all recognize that we have to pursue all possible options simultaneously at this point, and we all need to be interlinked. So let's keep in touch on that, and as I get something up, I'll see what I can pass on.
Yeah.
Great.
Well, yeah. If you could put together like just a half pager or one pager, over the next 3 years, I think $1.5 million would do this. That would be I'd love it if you could do something like that. And I imagine everyone on the screen here would love to see that.
Well, yes, I hope we can do it a lot quicker. Whatever. Let's move on, because I know there's some other people who want to. But let's keep in touch on that. Yes. No. I mean, this funding is badly needed.
This is exactly why I wanted to have time for this conversation. Maybe you can walk away with a possibility of 7 figures, but it's almost 45 after. Tom, do you have time to stay till the top of the hour?
Yes. No. Sure. I'll stay as long as.
All right. So for those of you who have to leave, we thank you for coming. But if not, we'll go at least another 18 or 20 minutes.
Yes, I'll hang on as long as you can stand it. That's okay.
All right, Robert.
Hey, Tom. Fantastic to meet you today. And I think what you've given us is a pitch for investment. And I'm really intrigued by the frustration that you described at the inability of potential customers to see the merit of the Biorock proposal, because it's something that's very simple. It's something that has got a very strong eligibility for carbon credits as a permanent verifiable means of removing carbon dioxide from the atmospheric system and the ocean system. And it's something that I would have thought that the tourism industry would be able to recognize, and also just local councils. You know, we've got all of these places with seawall problems, and you've provided a simple, sustainable solution that's that people really ought to jump at. And so, you know, you ought to be able to establish a profitable business. And it seems that starting off with, you know, identifying customers who have a business case and perhaps have the level of patience to see that that you know, doing something that will last is going to be better value for them than doing something that's just going to wash away. But yeah, like it's starting with those sort of customers, then you can expand onto areas that maybe have more of a philanthropic benefit. But it's this business model that seems to be something that's stymieing your progress.
Well, let me just say this. I mean, the business model of the hotel industry is to privatize the profits and socialize environmental costs. So any hotel will spend millions of dollars planting ornamental palms on their property, but they won't spend a penny in the ocean because that's common property that they don't own. And that's government's responsibility. So they in fact, it's astonishing that the only hotels we find that actually want to improve their own beach and reef through their own efforts are the ones that are locally owned by people who remember how it used to be. But I mean, most cases, you know, they destroy one place and move on to another. And so that they won't invest in the common property. That's a real issue. So that's held things back. Hotels that you would think would jump on it. I mean, most hotels have a dead reef in front of their beach that they killed themselves. And they have to take their guests hours by boat to see a few fish. And they could grow it back and restore the fisheries, you know, all around them, but very few are willing to do that. I mean, that's the, you know, because they don't see an economic benefit from.
But wouldn't they get more people coming to stay?
Well, you see, we've had in Indonesia two whole communities whose entire economy is based on people who come to see these reefs. Of course, tourism has collapsed, so now they're all out of jobs, and now they're out there shooting the fish, you know. But anyway, the thing is, we've found very few places that are willing to invest in their own marine environment because they don't own it. So that's been a huge problem. If every hotel were required to restore the reef in front of them, they'd regenerate the fisheries of their whole countries. They could do an awful lot, but they aren't, so they don't do it. So that's been difficult. With regard to the coastal protection, I mean, you know, for instance, in the atoll countries, what happens is they go to the World Bank or UNDP, and UNDP says, oh yes, what you need is concrete and rock walls. And so what they do is, I mean, for example, in the Pacific, it's all concrete Portland cement imported from New Zealand at enormous costs falling down. And that's what the foreign experts who are the experts for the development aid, that's what they all recommend. More rock walls, more concrete. They don't know anything else. And it's very frustrating, but they will not allow alternatives to be funded because that's what they know. So, yeah. We hope the Maldives decides to act on their own behalf, but so far, no country has. It's been enormously frustrating. Really.
So, thanks.
Yes.
Okay. Brew?
Yeah, Tom, fantastic. You've got to be one of my great climate heroes. But tell me, does this work on metal sheet pile walling?
Well, yes, it would. I mean, the thing is, those draw a lot more power. So, I mean, normally what we're trying to make is we're trying to make something that's open. But yes, no, we can do solid zones too. But you will basically be putting more electricity into small areas. Sure, but that could be done.
Have you spoken to the cathodic protection guys who are trying to preserve some of these metal sheet pile wallings in ports?
That's right. Well, the cathodic protection people are terrified of producing limestone. They call that, you know, that's what's the word? Anyway, they have a word for that, and they try to avoid that. So it's the same process that we're doing. We're just doing it at about 10 times the power level. So they say, oh, that's so much power, but you know, the benefits make it worthwhile. Yeah.
And what is the biological interface? You're showing pictures of oysters growing in relation to this. I can see you've got calcified carbon around your steel, but then you've got reef and shellfish growing as a result of it. They keep growing.
Oh yeah. Well, the thing is, actually, it's electrical field that stimulates them. So everyone thinks, you have to have them on the structure
Okay.
itself. No. I mean, so in other words, when we make the structures, the electrical field gets set up in the water. It travels an enormous distance, but we see things springing up all around the surrounding areas, corals settling and growing that we did not put there. So it's quite astonishing.
Got it. You didn't happen to talk to the guys at Sandy Lane that were trying to do an artificial surfing reef to protect the beach?
Sorry?
Sandy Lane in Barbados, the hotel there?
Yes.
They were trying to do an artificial reef to protect the beach and to keep the surfing going.
Well, you see what they've done. I know Barbados very well. I mean, I didn't know you knew Barbados. So, but yes, I mean, the thing is, the government has spent fortunes armoring the whole West Coast with rock walls, and that's caused the sand to wash away.
Yeah.
Now, Barbados is also one of the most bureaucratic countries in the world, certainly the Caribbean. And so we've been for 15 years or so trying to develop a shore protection project there. The whole beach is gone now at the place. So now they're down to bedrock, trees falling in and all that. And we hope to get permission to start in the next month or two after the beach is gone, but it's taken years and years of bureaucratic run around to get permission. This property is right next to Sandy Lane. Right next to Sandy Lane. It's a property right adjacent to it to the north. And now, so what's happened is people are spending money on stuff that isn't working, and they're not spending money on stuff that does. It's been very hard to do anything else.
Last question. Any impact in cold water? I mean, can we do this in
Yes. Yes. In fact, I mean, we have grown in all ecosystems. Wolf Hilberts even did projects below the ice in Norway and in Alaska. It does work. It works more slowly. I mean, the thing is, temperature affects the solubility of the minerals. But for example, I did a project with a Swedish student doing deep cold water corals and really growing at 4 degrees C. So it does work. I mean, control's a little more difficult, but it works with every ecosystem. So in cold waters, we grow oyster reefs and mussel reefs, not coral reefs, but it does work. And we can grow fish habitat even in places that are polluted where nothing will grow, or structural habitat for shore protection or other issues. Yeah.
Fabulous. Okay, well, I'll bring forward ideas and people where I can. Happy to.
Great. Other questions? I don't see any other hands.
Ron wants the question.
Ron?
I also just had one further follow-up, if that's okay, Herb, which
Sure,
was
go for
I
it.
asked, well, I did ask about the carbon credit side of things, and it looks like a fairly clear carbon credit as something that's permanent and verifiable, but have you been able to develop that dimension of the product?
Well, not yet. We're just beginning to talk about it. I mean, as you know, carbon credits is no agreed framework of what should be counted or how it should be counted at this point. I think you're right. Something like a rock is much more tangible than something that's ephemeral, like phytoplankton.
Yep. Okay.
Yeah. So yes, that will come up. But I mean, at this point, there's no agreement as to how to deal with marine carbon credits at all. And that's a bit of a bear because, how do you deal with the open ocean? Who's responsible for that?
Ronald, I think you had Ronald had a question or comment.
I think this group would learn a lot if you said a little bit about your role as a principal scientific expert for the rock dust group.
So, Ron, could you repeat that?
You're the head of the technical advisory group for the rock dust group. I've forgotten the exact name of the organization.
Okay. I'm not sure quite what you're asking, Ron.
The rock dust group.
Yes, but which one? Sorry, I mean, there's a lot of them. I mean, that's become very popular recently. But are you talking about Remineralize the Earth?
Yes.
Is that the group? Okay, well, that's the nonprofit organization. I'm actually their scientific advisor. That's an organization that's been around for a long time, and they're essentially promoting rock powders as slow release, long lasting natural fertilizers. And yeah, so we're working, of course, with biochar because the two complement each other perfectly. Biochar is not a fertilizer per se. It holds on to fertilizer in water. So the rock powder provides a source of the minerals to be absorbed by it and then passed on to the roots. Generally speaking, biochar and rock powder people work separately, but if they work together, they'll be much more effective.
Right, Leslie?
Yeah, I almost hate to do this to you because it's due tomorrow, I think, but there's been a call for proposals for ocean alkalinity through an Earthshot prize. I was digging for it. I'm not finding it on my desktop, but you might want to look those terms up because what you're doing is, right, you have an alkaline component to this, and you're certainly helping the oceans, and you know, take a look at that and see whether you could possibly put in a proposal in time. It's a pre-proposal.
Well, no, not possible, but thanks.
There you go. One day turnaround, but geez,
Yes, but
sounds like a fit. Yeah.
Again, you know, we haven't entered these competitions or anything. We're just trying to focus on getting the work done. You know.
I get it. I get it.
Yeah.
No, I think it sounds like you're working at so many different dimensions, and there's so many commercial and other possibilities for your work. And I suspect there's some folks either here on this call today or otherwise connected with us, you know, who may be able to, you know, to help and support you and work with you, volunteer their time, whatever. So, you know, I would certainly encourage you to, you know, send a note to the list or contact one of us and say, here are some of the things where, you know, we need some support and help. And I suspect you'd get a positive response. And so I just throw that out to you. I think we had a comment or question from you, Mr. Ship. I'm sorry, I don't remember how to pronounce your name. I'm looking at you. Go for it.
Yeah.
Yes.
I'm Chiduri.
Yes.
My question is, did you find any dolomite formation at all in those?
No, well, no, we haven't. I mean, the thing is, we're making magnesium hydroxide, and no, not yet. That would be interesting. But dolomite's not easy to make, you know.
Yes,
not easy to make at all. Yeah. So yes, but the magnesium hydroxide is metastable. So basically, in seawater, it would dissolve. We have to have very high pH to form that, and basically, what happens, it dissolves and gets replaced with aragonite, not by dolomite. Yeah, possible there are traces in it, but I don't know.
Sumitra?
Yeah, Tom's fascinating discussion presentation. I have been working with Brian von Herzen on carbon offset program and trying to get money investment on kelp and seaweed in terms of in Indian Ocean and Bay of Bengal area. And I wonder, you know, if we could talk offline, if you can see similar opportunities that could exist in those areas. But it doesn't have to be now, but maybe sometimes in the future. Because I'm working with them to do the framework, and Shell Oil Company is behind the investment, by the way. So it's not formalized. It's still trying to, you know, see how we can do this thing. So it's still very early stage. Maybe at some point we'll be able to do something with you. So maybe you can talk offline.
Well, let me just say this. I mean, general Biorock has really transformative possibilities for all forms of mariculture because we seem to grow everything quicker. Now, I've done a lot of work myself on algae mariculture, but not using this method. So we think we have very observations that very clearly suggest we're increasing the growth rate of the algae too, but on our reefs, they're being eaten immediately. So they go off into the fish food chain right away and they don't accumulate. But we haven't had a chance to really experiment with algae mariculture. And so, as I mentioned, you know, we are trying to put together a proposal with various people, and that's one of the areas we really want to look at. My focus is probably not going to be with kelp and offshore things as much as coastal algae in coastal ecosystems, because it's right next to land. And we really want to see that stuff rather than sunk into the deep sea. And with a delay, would like to see that recycled on land to bring the nutrients back onto land and increase more land productivity. I mean, but by and large, I mean, the thing is, I think the land has, and the coastal zone has a lot more potential for carbon storage in the deep sea, because it's just the net ecosystem productivity is a lot higher, and in the ocean, basically, you can't really turn the ocean to carbon sink unless you turn it into a dead zone. That's really, something people don't seem to realize. So
I'm not talking about the kelp and seaweed. I'm thinking your work, because it is doing the sequestration parts. So
yes, well, it would be sequestered if they were to turn it into materials or sequestered. So I mean, a lot of their proposals seem to involve sinking into the deep sea and hoping it stays there for a long time. Well, it won't. The thing is that they're bacteria and fungi that gobble that stuff right up. So it isn't good. But there's a long time delay by the circulation of the oceans. That gives you 1,000 years. If you pile it up on land, it'll rot and it'll turn back into CO2 pretty quickly. But on the other hand, if you turn it into biochar and pyrolysis, that will last in the soil a lot longer. It's not as long as wood biochar. Wood biochar is lignins, and that you produce black carbon, and some of that stuff can last thousands or millions of years. But the seaweed stuff doesn't have lignins, so it doesn't have much black carbon, so it decomposes quickly. It's chock full of nutrients, so it's a fabulous fertilizer. It's just that instead of doing one application every 20 or 30 years, you might have to do it every year. But that would be a way of recycling carbon back onto the land and the nutrients and being more productive. So that's something we're going to try to look at rather than the deep sea thing, because it's just closer to haul it off from the shore onto land than to take it way off into the deep sea and sink it. But the other issue also is making bioplastics from that material, to the extent that the thing is that algae are pretty much polysaccharides, and a lot of plastics are polysaccharide polymers. So there are some people doing. I'm not one of them, but I mean, I do know there are people trying to do a lot of chemical synthetic work using those as raw materials to produce materials that would last a lot longer.
We have something similar in mind. Thank you.
Yeah. So.
Okay, well, before we wrap up, I had a couple quick ones. First, I wanted to say that Reef Pomerantz is in our group, and he specifically asked me to make sure this was recorded, and he said he worked with you back in the 90s on coral reef issues. Is that correct, Tom?
Well, listen, it's an interesting story. Do give it my best, because yes, do give it my best. I tell you the story is quite interesting, because
Sure.
He arranged for me to make a presentation to Al Gore's Senate committee hearing in 1990, which is the first presentation showing that coral bleaching was caused by high temperature. I'd analyzed the satellite SST data, and he's the one who set that up. And then when Al Gore became vice president, Reif was then appointed Undersecretary of State for Climate Change in the Department of State. And at that point, we set up the Coral Reef Initiative. And the very first thing, it was a book I wrote on coral bleaching in the South Pacific. So he was involved right at the very beginning of that. But then what happened is that a political deal was made between the US and Australian governments, and they cut us completely out of the loop. So at that point, we never heard from them again. So yes, yes, but Reif, I understand, is working on polar issues now.
Yes. And
but the reason I mentioned that is that he played a really key role in getting the State Department to recognize that coral reefs were threatened by global warming, and that was an international issue that needed attention. But what happened is that whole process kind of got captured by people who, Noah wanted the funding, and they didn't want anyone else involved, and that so it all fizzled out, unfortunately, for political reasons. But he was right there at the beginning.
Well, so you're saying that Noah was the bad guy? The only reason I ask is their headquarters are literally across the street from where I live. So
well, I tell you, the thing is that when I analyzed the satellite data, what happened is that we tried to publish as a NOAA technical report, because it's all NOAA data. I was working with the people who interpreted the satellite data directly, and what happened is that our report was blocked by the White House for publication, because it said that global warming was already affecting ecosystems on land. So the White House would not allow that to be published.
Yeah. Well, what can we say?
Some things don't change.
Yeah, exactly. The history up one White House puts solar on the roof, the next takes it down, and it's been
Yes.
the story for 30 years now.
Yes.
I wanted to ask you one last question for myself, and again, if you're willing to stay and others are, I certainly open it up for continued discussion.
Sure. Why
And
not?
that is, I noticed in your little sort of signature block there that you wrote a book that was had the first word, I think, was geotherapy, which I love. I've actually wrote a book on new climate words. What is geotherapy? Did you invent that word? Can you
Yes. Well,
explain a couple
no.
bit?
It was invented by Richard Grantham. And
Okay.
this is his original, one of his original statements in 1991. And explain the point of view. Is he was a pioneering molecular biologist who was a professor in France and was pondering our destruction of the planet and the fact that we needed to reverse it. Otherwise, climate change and ecosystem degradation and extinction was really going to make the planet uninhabitable. And he as a scientist felt a responsibility to do something about that. And he invented the term geotherapy because, from a medical analog, he worked with a medical ethicist they invented the term geotherapy, and basically the view was that scientists needed to make a conscious decision to work on regenerating the habitability of the planet and to convince the politicians to go through with that. And it's not unlike your group here, but this was back in 1991, and we were trying to influence the UN climate change conference in Rio in 1992. So we put together an international team of scientists from many different fields, and very much like this group. And in order to try to make a statement that politicians might listen to. Well, they didn't, but they didn't listen at all, of course. And many people independently have seen the need and continue to do this. And so we have to keep pushing. But what happened here, unfortunately, is that Dick Grantham suddenly disappeared from the screen, and I never heard from him for a long time. It took me about 15 or 20 years to discover that he'd been struck down by some sort of Parkinson's disease-like syndrome, and he couldn't read, he couldn't write, he couldn't talk. His mind was sharp, but he was unable to function. And that sort of, the whole thing kind of collapsed at that point, but it's a forerunner. I mean, essentially the view is that we need to regenerate the natural mechanisms that stabilize our life support systems on the planet, the composition of the air we breathe, the water we drink, soil and food we eat, and that was his point of view, and I think it's the view of all of you here in this group too. So it's a convenient one-word term, in my view, for what we now call nature-based solutions. There's lots of other terms. There's a dozen different terms that people have, and it's all the same concept. It's that of actively trying to regenerate natural mechanisms. So, now, originally, what I did at that point is we regard as the opposite of geoengineering. Okay, and but now I recognize that geotherapy includes geoengineering and includes natural mechanisms, biogeotherapy from physical geotherapy, if you will, because we're all trying to work on the same goal. So I think
I will definitely add geotherapy to the next edition of my book, A Climate Vocabulary of the Future. Before we wrap up, and Paula was showing her copy of geotherapy as you were speaking, Tom.
Right? Yes.
And it's still available. Is it not, Tom?
And still relevant.
Yes,
It's
it is.
still relevant.
Yes, that's right.
And the Power for Climate has an article in it.
And Bio for Climate has an article in it.
Yes, that book is focused on soil nutrient regeneration, mostly with biochar and rock powders. There's 600 pages. It has examples of ecosystem regeneration every continent except Antarctica by different people, different methods, all different ecosystems, climates, and all that. There's actually a companion book on marine ecosystem restoration as well.
If you were a more aggressive marketer, you'd be putting a discount code in the chat so we'd all buy one. But...
Well, no, the publications I wish this was open access, and that it really isn't. We need to get the information out more easily. Sorry, Sumitra has a question, I think, but
no, I think I need to turn on my.
Oh, okay. All right. Well, maybe if there's one more question, comment, observation. If not, we'll wrap it up. Going once, going twice. Hey, thank you so much. I know I speak for all of us. It was amazingly exciting. And I guess the biggest takeaway I got was that we probably heard about 2% of the exciting stuff you're doing, you know, and you're working in so many different areas with so many different possibilities. And again, our goal is both to learn stuff, but to apply that to actually make the difference. Thank you again. We'll see you in 2 weeks.
Thank you.